Okay, so I'm going to do a quick Epanet review of the supply model and just show you some ways that um, this supply model can be improved for accuracy and clarity in the way it's modeled. So I'll start with the most important part I'm going to go over, and that's the treatment. How to correctly model multiple parallel chlorinators in Epanet. So the first thing I'm going to do is show an image or a diagram of chlorinators that we're going to model in Epanet. So that's not working right now. Here is the diagram of chlorinators that I'm working with. You have the pipe coming in, the bypass line at the top, the chlorination line at the bottom, and the water should go into each of these chlorinators evenly. Then join with the bypass line and go that way. So we're going to model the same way. Of course, we're only going to have 3 chlorinators in our model, but it's going to look like this. So we have, start with the bypass line going to the top. And the pipeline going to the chlorinators. And you'll notice, you may have noticed, all the chlorinators are vertical. Before I continue, I'm going to increase the node size to 4 to make it easier to move my nodes around. Okay, and I'm going to reposition these pipes. So you have the bypass line, it goes up, and then you have a bypass valve that controls the flow. And this bypass valve is going to control the flow between the chlorinators and the bypass line. So then you have a pipeline going from one chlorinator to the next on the bottom and on the top. So I'm going to move these pipes, shift them to the right place. I need one more pipeline to connect this last chlorinator. And the pipes in between the chlorinators can be very short. I'm going to put 0.5 meters in between each chlorinator. The diameter should be equal to the diameter of your pipeline. So this is a 3-inch pipeline, so I would use either 2.5 or 3-inch piping inside the treatment house. So I'll use 3-inch PVC. I would not go all the way down to 2-inch. You could use 2.5 since the flow is divided. But if you need 3-inch piping in your pipeline, then you need 3-inch piping inside your treatment house. So we'll make all the piping inside here to be 3-inch. These are 0.5 meter spacing. 0.5, 0.5, 79.2, 0.5. And this would all be 3-inch PVC pipe. This will be a little bit longer because it goes up and over, so it will be about 1.5 meters. And then the last pipe, after you go through the 3 chlorinators and the last chlorinator joins with the bypass line, and then it comes back down and goes out. I'll add a vertex here to make it look nice and neat. Looks like there were 2 pipes, so I deleted one. So this should be 1.5 meters, or really it goes over and down, but then it continues and goes out of the treatment house, so it will be longer. And this pipe can actually represent all the additional length of pipe that's inside the treatment house before and after the chlorinators. You can use one pipe to model all of that, just to keep your model more simple rather than having a pipe before and a pipe after. So I would make this 4.5 meters long, add some extra length, and I'll also put a loss coefficient to cover all the elbows and things inside the treatment house. I'll use a loss coefficient of 6. Okay, then you have this pipeline going over to the tank and this pipeline up to the tank. So now the last thing to do is do the details of the bypass valve. This is a TCV type of valve. It should be probably 3 inches, a 3-inch valve. That's about 75. And the setting is the number that is used to control how open this valve is. A higher number means this valve is more closed, and a lower number means the valve is more open. So a higher number will make more water go to the chlorinators, and a lower number will open the valve and make more water go to the bypass. And we want to get about 50 to 60% of the water going through the bypass. So I'll start with a valve value of 100, but then after I run the system, I'll recheck it. So before I continue, let's go ahead and run this system, and I'll show you how to adjust the valve. So here we have a flow of 141 through the bypass and a flow of only 87 through the chlorinators. So this needs to close more. So let's try 250. So now we have 122 through the bypass, 105 through the chlorinators. That's good. That's 55. That's 50 to 60%. See, total flow is 227. 122 divided by 227 is about 54%. So that's good enough. And you can, and that's how you model multiple parallel chlorinators in Epanet. Now I'm going to move on and quickly discuss the sump and some other things. This sump is modeled like a borehole, but it's not quite like a borehole. So the way I would adjust this, I would only have one pipeline between the sump and the pump. I would connect the... Actually, never mind. You can do it like this, because this, it shows, this model allows you to show the water level in the sump right here, the bottom of the sump using these 2 nodes, and the pump depth of installation using these 2 nodes. So that's good. The only thing I have to say here is it looks like this sump is modeled to have only 1 meter of water height, and I thought it was going to be higher than that. I thought it was 1.5 meters, so double check that. And then this would be the first pipe coming out of the sump. Oh, I will say this. Don't use a length of 1,000. I would prefer to see a length of only 1 meter for each of these. You want to make this pipeline as short as possible because it actually doesn't exist. The pump is in direct contact with the water. These other values are good, 1,000, 1,000. So 1 meter length. Okay, now the only thing I would change about this group of pipes here, we need to have a loss coefficient. There's going to be some elbows and some fittings there, so one of these pipes needs a loss coefficient. And then these two pipes can be combined. This 1 meter of GI and this 6 meters of GI can be combined into one pipe of 7 meters. So I'm going to do 7 meters here, and then put a loss coefficient of 8, 6 to 8, because you'll have lots of elbows around the sump. Maybe 6 is enough. The next thing, I can delete this line here. Delete this line. Make this pipeline go to junction 23. Delete this node. Make it just go straight. I'll let it go straight down. So the next thing I want to change, show you, is the water meter. It appears this is the water meter. If it's just supposed to be a valve, it's really not necessary to model an open valve in your Epanet. It doesn't have any effect on the system. But a water meter does have an effect. So I'm going to use this valve to model the water meter. First, label it. The best way to model a water meter is to actually get the curve from the manufacturer and put it in as a GPV valve. Go to your data, curves, and add your curve right in here, and then save your curve so you can use it in the future. You can call your, if it's a 3-inch water meter, which I recommend a large water meter for this project, 2 to 3 inch. You can just say water meter, or if you want to use millimeter instead of 3 inch, you can call it water meter 75. And put the same as the curve ID and put your curve in here, and then you can I'll just put it in now, and then you would paste the same curve code in the setting blank, and now you would model the curve. If you don't have a curve, that's fine. Just use the diameter, the internal diameter of the water meter. Let's say this is going to be, let's say this is going to be a 2-inch water meter. So it would be about 50 millimeters in diameter. Throttle control valve, setting 0, fixed status open, and then use a loss coefficient of 10. And that's how you can model your water meter. The next thing are the pipelines. My only comment on these pipelines is if they are long pipelines, they should be long in Epanet. I know you don't have much space, and one way to fix that is actually to model your supply pipelines separately from your distribution pipelines, and that gives you more space to properly model your supply line. And your supply line should resemble the KMZ. It should look like the KMZ so that the reviewer and anyone else looking at this file can understand what they're looking at. And also the length of the segments should resemble the length of pipe. It doesn't have to be perfect, but something close to help us understand what's a long pipe and what's a short pipe. So here we have 200 PN16, 200 meters of PN16, 300 meters of PN12, 1,500 meters of PN10. I would combine these two pipes, but it's not necessary to do that. So I'll just lengthen these lines a little bit to make it a little more clear that they're longer pipelines. And then this one is the longest, 1,500. Something like that. Okay, so those are the corrections I would make to this Epanet to make it more accurate.